Hey all, hope you all are doing good. Welcome to my channel and welcome to the LLM playlist. So in previous session, we have learned about the LLM, the basics of it, the overview of it, and as part of transformer architecture, this one, we have learned about the transformers, the inputs, outputs, the full flow. A continuation of the transformer architecture is two topics. One is attention layer and one is MLP layer. Okay, so we are going to cover today the attention, and in the next session we are going to cover about the MLP layer. With that, we are good with the transformer architecture. So the first three topics are covered as part of today's video and next video. So with that mention, let's get started. One point to highlight, it's the attention layer is all about the one game. Just like how a human plays, machine also plays. What is that game? What is the math behind it? Let's jump right onto it. So before we start the attention, what is a prerequisite? Attention is all what you need. So there is a paper on that. Let me bring it on. Attention is all you need. Is literally a paper where everything about the attention layer is mentioned so neatly, so deeply. I will keep this link from where you can read it in the description. And before we get started with the attention, let's recap for 1 minute. Okay, so what we did previously is what we understood is what is embedding. Okay, then we understood what is a lookup table where embedding is projected without any context, without any meaning, and then how do transformers add, how do it converts by making use of transformer layer, attention layer, MLP layers, and which part of the complete flow do we actually call LLM? Does tokenization comes under LLM? Does the output given comes under LLM? All that we discussed, and why the context matters. All that we discussed previously on the transformer session. So if you have not seen, let's go right into it. So what is a core idea of attention? It's basically 6 steps. Okay, so it basically start with the point where the token begins without any context, because the context will be given in the attention. Okay, now what attention does is you have a sentence. Okay, we'll keep the sentence horizontally and we'll keep that sentence vertically, and then attention will tells us how much attention does each word needs to pay to the other words. I hope you get it, and we'll see all that in examples within a minute. So this is just a gist, and then short and long range information flow. So for example, you have 400 pages of book. Now you are reading the complete Sherlock Holmes the novel, and at the end, oh, so this is why the thief was blank. If I want my LLM to answer it, it needs to understand the information from the first page till the 400th page. So how that logic, that context, that English, the sentence, the tone, the semantic, the grammar, everything it knows is what the short and long range information flow. And this was a third step, and these are the next three steps. So how it gets the tone, how it gets extracts the meaning via context, because whatever we are saying, it does it mathematically. All right, and then we are going to see how MLP contribute to it. This is what we are going to learn in the next chapter, because overall the context that it needs is together with attention plus MLP layers n number of times. Okay, and finally it will do the prediction. I hope we are clear with the attention, the core idea. Okay, so the basically this prediction of the next word, okay, is done by attention and MLP layer. We understood. Now in attention we have multiple ways of doing it. So one of them is single head of attention, multiple head attention. So we are going to look at single head attention, and as a continuation in today's video itself, we are going to learn about multi-head attention. So let me give you a core idea of what is a single head attention or multi-head attention. Overall, the math that you see on my screen, we are going to go into details of it. So this is a bit mathematical today, but let me keep it in a very simple manner. Okay, so here is the thing. If you are playing a game, you might have played this many times where let's say you are one participant, I am one participant. Okay, and you thought of a dish already. Now I have to ask you questions. Let's say I am given only 10 let's say 10 chances. I have to ask a question, and then you will give me some answer. Based on that, I will ask you one more question, you will give me some more answer. right? So that's how we reduce and we reduce, and I try to reduce the options, what I can predict. I will try to reduce, and let's say after the fifth question I understood that it's a food. So, I'm narrowing down. First time when I'm asking you the question, is it a vehicle? Is it a food? Is it a person? Is it an air? Is it a planet? So, I'm reducing that after every question. So, that's how at the end I am left with one option, that is the answer. Okay, so that's how the question answer games. Okay, and which one should I consider, which one should I not, all that question answers we is what mathematically happens to predict. So let's understand that. And as I mentioned, today the sentence that we are going to take an example for all our topics is: the hungry brown fox jumped over the sleepy dog. Okay, so the hungry brown fox is what the sentence is, and we expect our LLM to predict the word called jumped. Okay, that's what we are planning to do with all our example. Okay, so this is what overview of single head attention is. Let's jump deep into it. So the first thing is build the query. So let's spend 1 minute on this, and then I'll take you to a figure where you can map your understanding. When we say build the query, so here query is represented with Q, and we will have a query matrix, which is a weights, that is tuning parameters, and then we'll have a query vector, which is a result of your multiplication. Okay. Similarly, here query matrix by word itself, we can say it's a list of questions. Okay. And step two, we have keys. It's keys is nothing but answers. Okay, the solutions, the things that we are getting. So keys we can consider it as a answers. Okay, now then we will give score. So based on the question, based on the answer, we will decide how relevant it is. Okay, and how much weight I should give it, basically how much attention should we consider give it. For example, we are talking about what is the next word after fox. So fox is our target. Okay, but should I to predict the next word, should I give more weightage to the word called the, or should I give more weightage to the word called hungry and brown? So that attention, okay, that relevance, okay, and the normalizing it, all that we'll be doing in the scoring part. Once the scoring is done, then we will give values to the words which we think is relevant, and this is how we will update the embeddings n number of times. So these are the four steps, and finally updating the embeddings. That's all is happening in single head, and let me deep dive into each of the steps. So first thing, we'll deep dive into the query, the question matrix. Okay, so what happens, what is the idea? Basically a fox, okay, is our target. Okay, and the question that we are preparing is, are there any adjectives before me? So that's the question I am asking. Okay, so first thing, when I say I am asking, how will the LLM ask it? So the way LLM ask it is, it will have a weightage of, it will have a matrix, okay, only for query. Okay, and we'll call it as query matrix. It's basically underscore q, meaning the weightage or the parameters of query matrix. Okay, so embeddings, as we discussed, that each word will have a vector which will be represented with a vector, and it is placed into a vector space, and it is, that's why it is called embedding. So when we multiply the embedding with uh, the question matrix, we get question vector. Why I'm saying question? We'll use the term called query. So on multiplying the embedding of a word with the query matrix, we get query vector. Okay. Now there are 10 words. Okay. Will I ask the query only to the same fox? No. I'll ask the same query to all the words. Okay, so the idea is we are going to a matrix multiplication. Conceptually, we are, the LLM is going to ask a question to a word. For example, are there any adjectives before me? Okay, and the operation that we are doing is we are multiplying the query matrix and the embedding. Okay, so why are we doing that? So it will encode what the fox should look for, because in before we enter to this topic, I told you query matrix, that is question, key matrix, that is answer, value matrix, that is relevance. All these mathematics at the end will give you a solution saying how much attention should I give for a word. Okay, should one word give for the another word, not I give. Okay, and then we will compute the qi, that is the query vector. So if here I did e4 and I got q4, similarly I will do this multiplication with all the words, so I will get qi. Okay, I hope the first matrix you understood, the weightage question. Okay, so here, if you see, when I do a multiplication with each embedding, okay, this weightage Q I'll apply to each of the embedding, and I'll get query 1, query 2, I mean query vector 1, query vector 2, query vector 3, query vector 4, like that. Okay, so that's what we are going to get here. Now, what are we going to do with this? So to answer that, let me go back a bit previously. So let me go here. Okay, let's say you are ready with all the query vectors, and that vector is represented here on the top in the column. You can see my cursor, right? The query vector will be presented here. Similarly, let's spend 2 more minutes in getting the key vectors also, and that key vectors will keep here on the left hand side vertically. So query vectors on the horizontal, um, the key vectors on the left hand side. Finally, we'll do the multiplication of both and we'll fill those values. Okay, don't worry if you didn't understand. As of now, we generated query vector with the multiplication of each embedding and its query matrix. Okay, so we are good, we are ready with the query vector. Okay, now let's focus on the step 2. And step 2 is keys vector, which is basically answer saying, hey, I am an adjective, answered by who? The hungry. Answered by who? The brown, or not the brown, brown. Okay, so let's go to the step 2, which is key vector. So what is key vector? What is the idea? It basically is going to answer the question. What was the question asked? Hey, is there any adjective before me? Okay, so when I say key vector, it's basically it will say like hungry and brown words will emit a vector saying I'm an adjective. Okay, signals a noun. Okay, so what happens here, the operation that we did is similar to the operation that we did with the query. Okay, so we are going to multiply each embedding with that of key matrix to get the key vector. You can see it's similar. This is our weightage for the key matrix, and this is we are going to multiply with each embedding, and we are going to get key vector 1, key vector 2, key vector 3, like that for all. So key vector 2 is basically I am an adjective. Key vector 3 is basically I am an adjective. Okay, so why are we doing this? We understood that it needs to, so conceptually we are saying it is answering. Okay, but mathematically what is happening? Previously we understood man, woman, king, a queen. It's basically this complete space is a vector space. Okay, and there is a word here. Now this key vector is basically pushing the word into different direction, and finally that's how we get the relevance of it, based on the direction, based on the comparison, based on the dot product result, based on the positive negative direction. All that will happen in the vector space. Okay, so what is the scope of it? The scope of it is basically pushing into the vector space. If we read this, we compute a ki for every token using the weight matrix. Different heads learns different advertisements. The same question will ask to a different embedding, and that too multiple times. We will see when we say multiple times. As of now, I'm saying single head means one time I'll ask. One time I'll ask one question, but one time only I'll ask 10 different questions. So let's say I am playing one time with one head. I'll ask you 10 different questions. Okay, so after this we are going to see multi-head attention, where we'll ask multiple times. As of now, I'm asking one, but I'm asking the same question to all the words. Okay, so we are good with the key vector, we are good with the query vector. Let's go to a previous slide once again. So we are ready with the vectors that we need on the top. We are ready with the vectors that we need on the left hand side. Okay, so what do you think will be the next step? This, if we see here, step 3. Now we start scoring it. So do you see dot product q? We will do between the query and keys. Okay, let's go to our slide where we'll be understanding about the step 3. Okay, there are very less steps, and if we understand once, we are good. So no worries. Okay, so what we do in step 3 is basically we have a query matrix, query vectors, we have a key vectors, and then we are going to do a dot product of them. Okay, so when we do dot product of them, we get different values. So here k1, we did dot product with q1, we got some value. K1, we did dot product with q2, we got this all value. Similarly k2, and that's how we fill this matrix. I hope you are getting it. Okay, the first thing we did was a dot product. Okay, now this value will be in various ranges. Okay, so if you understand that whenever we are dealing with any modeling or any, we want to make sense out of the data, what we try to do is we try to normalize it. Either we try to bring it lower ranges, because the lower the ranges, the better it is to capture the relevance or any analysis. Okay, so to do that, what is done is, so first thing, you understood that we did dot product and we fill out this all values. Next, what we are doing is we are dividing it with the square root of the dimension of the key. Okay, and that we are passing it to softmax. Now if you know what is softmax, it does a normalize. Okay, so it brings a value between I think some would be 0 to 1. Yeah, it is between 0 to 1. I just double checked. Okay, so what happens is all these values together would be between 0 to 1. Now you see the value here 1.2, 1.0, you are saying it's not between 0 to 1, right? Yes, because it is the value that we get after doing the dot product. Okay, now if you see this is 0 0.3, right? Now after the softmax is applied, we see this value becomes the fox value. The fox value becomes 0 0.17. Okay, if you see the hungry with fox, it's 1.2. Here the hungry becomes 0 0.37. Okay, so basically it normalizes all the matrix values such that the range is between 0 to 1. Okay, so why did it, because to normalize, to get more sense out of the data. Okay, so if we see the same thing once again, there was key vector, query vector, and then we multiplied it, and then we got some value, and then we applied softmax function on it, dividing it by the square root of the dimensions of the key. Okay, and then we get this value. Now why we are considering only this value? There's one more thing, let me highlight it. Okay, what are we doing now? We are training our LLM, right? So when there is a word called the, it should be predicted based on all the words that is towards left of it. That means the words which are already came in the sentence. We don't want to predict the based on the words that are going to come next, because that's not what is going to happen in a real world. You need to predict, so you don't know what is the next words to it. Okay, so everything that is towards the right, that is hungry, brown, fox, whatever words, we will make it blank, or we will try to remove it from our scope in the vertical. Let me repeat once again. So if I want to predict the word called the next words of it should not help me with the training, right? If it is helping with the with if it is helping me to predict my current word, that is, if the next set of words is helping me to predict the current word, it's basically cheating, right? So that's why I'll try to remove that as part of training. So how am I removing it? By making all those words which my current word should not consider as blank. Okay, how am I making it blank? I will tell you in a minute. Similarly, all the words that is towards the right of hungry, yes, brown, fox, jumped, everything, so those things I will make it blank towards down. Similarly brown, similarly fox. So the pattern that it forms is, if I draw a line diagonally, all the below matrix will become blank. Okay, now I am telling you conceptually that we will make it blank, but how do we make it mathematically? To give you that understanding, softmax, as I said, will apply softmax on each of the column. Okay, now when I say each of the column means I will pass this complete vector. You can see I'm highlighting this complete vector, and I will pass it to the softmax, and then it will going to normalize it. So when I'm going to pass all these things, I want somehow that this value should become 0. The one that I want to make it blank, I want in my final result that should be coming as blank. So to do that, I need to update these values that I want to blank it out with negative infinite, because when we normalize, if it's negative infinite means it will come close to 0 after the softmax try to normalize it. Okay, so that's how all this will become 0. And there's one more thing. So once let's say this becomes 0, Okay, the values that it is trying to normalize, the summation of it would be approximately 1. Okay, so if I give you an example, let's take this Fox one as an example. After softmax is applied, these are the values that we are getting. Now if we sum 15, 37, 32, 17, I think 14, 15, 19, yeah, it is approximately close to 1. Okay, so that's how softmax is. 1, it normalizes. 1, since I'm passing this complete thing as an input, the summation of this would be approximately 1. So let's try to rephrase it in one sentence. We passed, first we created the dot products, then we blanked out all the things that we don't want our training to consider, okay, with by updating the values with negative infinity, and then we are passing all the column values to the softmax so that it normalizes, and the one which you don't want to consider, it will make it 0. Okay, so that's what we are getting as part of scoring and masking. Now if you see in this complete matrix, it's mostly not relevant, so 0. The bigger the value, the more relevance it is. The lower the value, the less relevance it is. So if we see, these 4 have a good value. This is just an example values. Okay, now if I go to the next slide, okay, the bigger the value, the more relevant it is. Okay, now once this level is done, once we are done with step 3, now I want to reduce the complexity by saying we don't need key vectors, value, query vectors, key matrices, query matrices, nothing we need. Just erase it from your mind. Okay, so what did we got finally after doing these 3 steps is we understood how relevant one word is with the another word, how relevant hungry is with the word the, how relevant hungry is with the word brown, how word hungry is relevant to fox. Since it is more relevant, you see more value. Okay, but I don't want values anymore. I understood it is relevant, so I'm going to replace it with something called bubbles. Okay, the bigger the value, the bigger the bubble. I think you understood. So with this, what I can understand, sleepy word is relevant to the word called dog. Okay, so this grid, this matrix where I know which word is relevant to which other word, that matrix I will call it as an attention pattern. I hope you understood. I asked a few questions, I got few answered, and then I applied some operations, some thinking, some vector movements, and in conclusion, I understood what is the things that is relevant to each of my words. Okay, which word is relevant to what? Okay, all right. So mathematically, what all happens, I kept in the statements. You can go through that once again, and the things that we discussed in previous a minute back, all that I kept in sentences here for your reference. So you can pause and give it a go through once again. But what we got is the attention pattern. Now let's understand one more thing. Okay, when you are using, I think we discussed in this previous session also. Let's give it a thought once again. So this attention size, if you think in a human brain, we can say this is what I can focus on, this is what I can understand. So what I want to say is, in any LLM, context size is as same as that of attention size or attention pattern. Okay, that's why you see when you were using GPT-3, that time the context size was approx, I think 2048. Yep, I just verified. So in the GPT-3, the context size was 2048 tokens. Okay, that's why if you do more conversation in a single session, while it is answering your 100th question, it might forget first and second question because it is limited by its attention pattern. Now, as the GPT models are increasing, the context size are trying to increase. Okay, and how to deal with this limitation? Okay, one thing, we did few steps, we got the attention pattern. Now what to do with that, what is our next step, we will understand by giving 1 minute of break. In meanwhile, attention, our context size that our model can deal with is same as that of our attention size. Okay, now attention size is restricted by its own limitations. So how or what I can do to improve my context size? Okay, there are few patterns available, so I will list it out for you here. You can see sparse attention mechanism, reformer, ring attention, long former, adaptive attention spans. There are few things. This is not in scope of our video, but there are few patterns that is trying to solve the issue to improve the context size more than that of attention size. Okay. So with that mention, let's get back to our original thing. That is the final step where we have to update our embeddings. So what do you have so far? This operations, okay, I won't speak that because otherwise you will sleep. So let me speak in terms of diagram and then we'll come to this slide so you can understand it better. So if you see what is happening, let me go this, yeah, this is a better understanding. So we have a vector 1, no, it's we have a key vector, we have a query vector. Okay, but now we don't need anymore. Now we are talking about value matrix. Okay, let's see this, the values that we got previously. For example, if I go back here, you can see after softmax is applied, here we got one value 0.14, 0.42, 0.36, 0.08. This is where this is there in the attention pattern. Okay, now what we are going to do is we'll forget key vectors, query vectors, and now we are thinking about something called value matrix and value vector. Okay, what is it? Let's try to understand in a minute, but that's our final step. Okay, so what we are going to do is we are going to put all our value vectors, no, value matrices on the left hand side. Previously it was key matrices, right? Now we will put value matrices, and what we are going to do is we are going to multiply the value matrix with that of the corresponding value, and that value is what we are calling weightage, because we understood the three steps that we did was to understand the relevance. So the more relevance it is, the more weightage you will give. So we will multiply that weightage with that of our value matrix. So that's what we are doing here. Okay, so if you see 0.14 was the relevance and we multiply it with the V1. Okay, now what is V1? If you see V1, no, it's V1, V2, so it's basically Vi. Vi is nothing but um, a result of a multiplication between your embedding and your value matrix. Okay, so here you multiplied your embedding with the value matrix, finally you got the value vector, and that value vector you will multiply with the weightage and you will get some values. I hope that's clear. And these values you have, right? What you will do with that value? You understood, right? What we did, we multiplied the embeddings with the value matrix, we got the value vectors, we multiplied the value vectors with that of the weightage, and then we got some values here again. Okay, what we are going to do there? So for example, let's talk about this column only, and the same thing will repeat for the other columns. So what we are doing here is we are going to sum all the values. So all the values in the sense the context that we had relevance. Okay, the relevance multiplied the value vector, the relevance multiplied the value vector, the relevance multiplied the value vector. We'll sum all it up and we get something called C4. Let's call it at context 4. Okay, so if I speak that here in this diagram again, we are now going to sum the result of this plus this plus this plus this across the column. We will do until where these grayed out ones we won't consider, because that we kept negative infinite and softmax made it 0. This we kept just for understanding purpose. Okay, and you can see it's all 0 as of now. So we will sum it up. Okay, similarly, so that summation is nothing but the delta E. So the summation will give us context 4, and that context 4 we are going to call it as delta E4. It means this is going to tell us what is the change that I should do to this embedding E4 in the vector space to become more relevant to predict the next word. Okay, let me repeat this word again. Once I do the summation of these values, I would get C4, that is context 4. I will also call it as delta E4. Similarly, I will get delta E3, delta E2, delta E1. Now what this says, what this delta says is, you need to update your current E4 with that of delta E4 or C4 to give more relevance, to give more context to predict the next word. I hope you understood. Let me show it here. So after the summation, I got C4. Okay, let me see. Similarly, I will, yeah, this is just one more representation. Yeah, so you see, I got delta E1, right? So what I'm going to do with my delta E1, I'm going to do even plus delta even, which brings my new even. That is, I'm giving a new space to the embedding 1. I'm giving a new space to the embedding 2. So let's say previously this was the fox. Okay, this was fox. That is E4. Now I added delta E4. That is, I added the context which said that there is an adjective called hungry, there is an adjective called brown. So when I give all that information as part of delta E4, it becomes a new E4. Okay, now it looks different. The updated fox with the context applied. So I had fox originally. Okay, now I moved it with what? With the delta E4 vector, and now it becomes a hungry fox. Now it becomes a brown fox. Okay, so that's what the update we are doing. This we are going to do with all the embeddings. Now here we understood the example of fox, but similarly we'll do with the brown, the hungry, and the also based on the relevance. You can see the dog has a relevance with the sleepy and the dog itself. So, and with this grammar as well. Okay, so each will be updated. Dog is E9, so E9 will be updated with E9 plus delta E9. So what we did so far is called single head of attention. I know it's mathematically a bit, I don't know, overloaded for this some time that we spent so far. But yeah, that is how we are updating the RMDs. Now here we did single time. Just remember, we asked the question, we got the keys, and then we got the relevance, and we applied dot product, and we updated our MDs. This completes 4 steps is called single head of attention, as I highlighted below. All right. Now, uh, before we jump onto the multi-head of attention, let's do one small mapping, which we did in previous session also. So, in this session, we came across key, query, and value. Now you know that we have total this many weightage and this many matrices. So these are the dimensions that we calculated before. So now what new things we got? We got dimensions, that is 12,288 dimensions of the GPT-3, and then we are multiplying it with 128 because the matrix is of that dimension, and then we are going to create the dimension in such a way that key and queries are matching, and then later on we have to do the multiplication, matrix multiplication with the values. So the dimensions are something like this: 12,288 into 128, 12,288 into 128. These were on the column side, these were on the row side. Okay, now if we are going to multiply it with the value matrix, the dimensions that we should be aware of it, it should be this and this, right? But it's not the case. The value matrix that we taught is made up of two matrices with 128 into 1228 and 12,288 into 128. Okay, so these are the dimensions, or we can say these are the number of tunable parameters or weightage we are talking about. But this is not enough, there's much more to you. Don't worry, you want, you go take a break and come back again. But let's move on to the multi-head attention. This is not filled yet, just for your information. We have 175 billion parameters. Okay, so let's go to the next slide. And multi-head attention, again, just like how I explained single head of attention, then you, if you see the operation, you will understand. Similarly, I won't okay, let's see this. What are we doing here? We are multiplication of, okay, let me not go through this because once I explain you the concept, this is understandable. So here what we did, uh, we got delta E1. Okay, if you recollect, okay, pause for a minute, and if you think, we got the update that we need to do to the embedding 4. Let's take an example of embedding 4 because the same thing applies for all other embeddings. So we understood what is the update to the embedding 4 we need to do from one head of attention. Similarly, I will get the context from different single heads of attention. Okay, and then I will add all the context and I will get more context. The more the context I have, the better it is, right? So here what I'm doing is the key, query, everything that I did. Okay, I got the delta E, okay, from single head. Okay, so these three boxes together form single head of attention. Similarly, I will apply with the different questions, different answers, and I will get delta for that embedding in all the layers. Okay, should I say layers? No, I should call it blocks. I'll tell you why. in a minute. Okay, so in one block there will be multiple attention head. So when we say multi head attention, we are talking about one block. And what is the meaning of block, you will understand in a minute. Okay, so in the LLM you will have multiple layers, and in each layer you will have blocks. Okay, I hope so. If we come from top, LLM will have multiple layers. Let's say LLM has 10 layers. Okay, and in the first layer we are having multi head of attention, means in the first layer we will have uh, multiple times single head attention. Okay, so when we say embedding, the change in embedding 4, one in single head gave me this, one more head gave me this, one more head gave me this, one more head gave me this. All this context I'll to take and I'll update my embedding 4. That happened multiple times in one layer. Okay, so this multiple times together becomes a block. So here I can say my block contains 4 heads of attention. Okay, now if I have 20 layers, I can have 4 head of attention in layer 1, 4 head of attention in layer 2, 4 head of attention in layer 3, like that, so on. Okay, so here you can see my embedding will get updated with the current embedding plus the deltas that I am getting from the each single head of attention. That's why I call it a multi head of attention. Okay, so let's see the idea behind it. Different heads will give you a different context, right? One will give you the tone, one will give you the semantic, one will give you the dictionary meaning, one will give you the relevance. No, all together will give the relevance. Okay, and the best part is all these heads will think parallelly. Okay, so that's what multi-head attention does, and we took an example of 4, but in GPT-3 we have 96 heads. Okay, so in one layer we have 96 heads. If it is having 100 layers, it means 100 into 96 heads it will have. I hope you are getting the picture. Okay, so you see the dimension that we kept in previous slide, now we are going to multiply with the 96 because in each layer it has 96 heads of attention. So all these weightages will be multiplied by 96. That's not enough to add to your complexity. Okay, now let's see what is output matrix. This is last step. Okay, so this is nothing new. This is a new topic, but I'll tell you that you already know what is it. Let me go back here. Now if you see, we know what is value matrices, right? Now value matrix is made up of two matrices. This is first matrix. Okay, this let me see, pen, yeah. So this is first matrix and this is second matrix. Okay, this first matrix is something common for everyone. Okay, for every answer or every question. Oh, no, let's say this is common for all the embedding. Okay, this will change for each embedding, so I will call ei embedding I. Okay, this is a value matrix of each embedding, so this will change for each embedding, but this will be common for all. Okay, so when we say common for all means it should be present somewhere, right? So it is present in output matrix. Okay, it is different for each head, but it is common for all the embeddings. Okay, so let me bring it here. Okay, so if you see here, here it is not there. Let me see, where can I get it? Value. Yeah, here it is. So when you are trying to get the value vector by making use of value matrix, so this is part of two matrices. One is the output matrix, okay, and one is the, what do we say, the actual value matrix. Okay, now if I say there is a big matrix, okay, in this big matrix you have matrix 1 here, matrix 2 here, matrix 3 here, matrix 4 here, 5 6 7 8 9 10 11 12. Okay, so in this big matrix, this is called output matrix, but in this big matrix the matrix that you are using here will be, let's say you have what do we say, let's say you have 10 heads, no, let's say you have 12 heads. Okay, so each head will have its own output matrix. Okay, all the output matrix of all heads together forms output matrix. So here, let's say you are dealing with your head 1, so you will get the output matrix head 1. Let's say this is head 1, and you will have your own matrix. Together you will form the value matrix, and you will apply the same value matrix with all the embeddings. Okay, so to simplify it once again, right, overall you had value matrix previously, and you are multiplying it with your embedding to get the value vector. But there, this value matrix was made out of the output matrix and the value matrix, and this output matrix is specific for each head, same for all embeddings, but specific to each head. So if you have 96 heads like in GPT-3, it means your output matrix consists of 96 small output matrices. Okay, I hope you got what is output matrix. Now don't worry if you don't get it, that's fine. Okay, so you can see this this is value matrix, this is also value matrix, but theoretically when we are speaking, when we are talking, when we are documenting anything, the first one is basically from the output matrix, the second one is your actual output matrix. Okay, so all this uh, output matrix of all the heads together form something called as the actual output matrix. Okay, uh, now with that mention, I we understood what is relevance, what is the delta that we are getting with one head, the delta that we are getting from multiple heads, and that value we are using to update our embeddings. Okay, so this much context we got just from the attention block. But is that sufficient? No, it will go through multiple layers in between. So what is that layer? In the transformer layer, the embedding, the tokenizer, no, the tokenizer, the embedding, then the attention block, MLP layer, and few normalization layers. So all this layer together will help us in predicting. Okay. So today we understood about attention layer, single head of attention, multiple head of attention, and yeah. So let me do one more thing. We understood one thing, that in one layer there was 96 heads. Okay. Now, how many layers does GPT-3 has? If I go to this slide, you can see GPT-3 has 96 layers also. Okay. So in one layer, we had 96 heads. Okay. So in 96 layers, how many heads do we have? We will have 96 multiplied by 96. I hope you got it. Okay, so we have 96 multiplied by 96. Okay, so just imagine now by what range the dimensions will increase. Okay, now if you see in each layer there is something called MHA, MLP. So these are the layers which are also helping us to get more context. Okay, so we are going to talk about MLP in the next session, but overall I hope you are understanding the transformer architecture so far. We understood the full flow, we understood which piece is LLM, which piece is not, we understood the transformer, we understood the attention today, and in the next session we are going to understand the MLP. Okay, and yeah, that's all. Let's see this one thing. So now we got, previously we had 96 heads per layer, now we have total 96 layer. So all this got multiplied with 96, 96 more. Now you see total how many parameters we have? 175 billion parameters. Okay, but if I sum everything that I have on my screen here, okay, how many parameters we got? We got 58 billion parameters. Means after doing this much also, we reached only 1 by third of the complete parameters that our GPT-3 model uses. Okay, so it means what? It shows the criticality, the importance, the heart, or the, yeah, basically the criticality of the MLP layers. So you see, out of the complete parameters that GPT-3 uses, we were only able to cover one third of the total parameters. So in the MLP layers, that is this layers, we are going to have two-third of total parameters. So if you are interested, do mention in the comment section, and we will learn about MLP layer in the next session. With that, we will complete our transformer architecture and we will start on the frameworks. So hope you like the session, and if anything you want to do corrections or anything, do mention in the comment section. One more thing I want to say is I am, yeah, do give a read to this journal paper, which is attention is all you need. And so in the next session, let's try to explore an MLP, and we'll wrap our transformer architecture with that. And one last line before we leave is, these first three videos we are taking some time on the mathematics. So that's why it is possible that you might find it a bit complex, but don't worry, after we are done with this architecture it will be very simple. So with that mention, hope you have a very good week ahead. So do mention if any feedback, if any correction, if any suggestions as well. Thank you. Bye bye. Also do follow and subscribe.